Hi and welcome to Allen High Schools. This should be our last video unless I can do some AP-like free response for you. But for now, we're going to move into our last type of bonding, which is a coordinate covalent bond. This is at least for testing prior to 2013. So if it's after 2013, we're not going to be doing reaction predicting quite the same way. So this is up to 2013. This is a part of reaction predicting as well. So we need to get into some definitions though. In a coordinate covalent bond, often called I don't know why, but it's often called a dative bond. It's a covalent bond in which one of the bond participants supplies both of the electrons. So up till now, in a typical type of a bond, we'd have X and Y sharing two electrons to form a bond, but they would have each brought an electron into the marriage, so to speak. In this case, one substance is bringing both bonds, so both of those electrons came in with the nitrogen. Now, the substance that brings in the electrons, so the Lewis base, is called the electron pair donor, and the Lewis acid is the electron pair acceptor. So the acceptor and donor is switched from your typical acid and base. All right, so a metal ion, an ion such as H+, or an electron deficient atom, acts as a Lewis acid and accepts electron pairs. And what's called a ligand, it's a group with a non-bonded pair of electrons. We're going to see things like chloride, hydroxide, water for that matter, cyanide, and so forth. We're going to see a variety of them in the next slide. But just to give you an idea, what they have in common is they have pairs of electrons they're willing to donate, and those ligands are called the Lewis base. Now, we have a coordination complex. That's a complex ion. You'll see some in just a minute. I think it'll be clear, with a counter ion to balance charge. So a coordination complex is neutral. Now, the coordination number tells how many ligands a substance can accept. All right. So, for example, I've got some pictures in the next one, so let's look there. Here's some pictures. Sorry, they're smaller than I would have liked. But if you notice here, we've got water, so the OH2 or H2O, that's acting as our ligand, and the iron is acting as our Lewis acid. It's electron deficient. That iron, that's an Fe+3 or 3+ ion, right? And notice that it has 6 waters on it. That number 6 is the coordination number. Okay, now I used to think these were really hard until one of my students, because I really didn't pay much attention to them. So for a long time, I could just teach my students how to avoid them, which was really stupid, because once you get the pattern, they're really easy. If you notice here, silver has a charge of 1 and a coordination number of 2. Copper has charge of 1, gold charge of 1, and we can do 2. Do you notice that we're allowed to? I mean, there's other options, but certainly we can just double the charge. So we'll use the 6 for aluminum, but we'll use the 4 for these. So we'll just double their charge. And there's one exception. Iron +2 has a coordination number of 6. So other than that, we can just double the charge, and that's how we can find out how many of each of these that we have. So if I took, say, my aluminum and I added hydroxides, there's a number of products they'll accept, but probably the most common, if there's excess hydroxide especially, aluminum ion, has a +3 charge. So I'm going to double that and give it 6 ligands. So do you see what I did? I took the charge, I multiplied it by 2, and that's how I figured out my number of ligands there. So I'd need a 6 here. Okay? Now, for the most part, we're not seeing a change in oxidation number. And let me backtrack here because I didn't balance my charge. The aluminum is +3, the hydroxide's -1. Since there's 6 of them, I have 6 negatives. So this has a 3 negative charge left over. Now, if I wanted to get the complex, this would be called the complex ion. If I wanted the coordination complex, I might add something cheap like sodium to be a positive counter ion to that -3 charge. Okay, so that would be now the coordination complex that we discussed above. All right. Now, there's a couple of exceptions here that you will need to memorize. So let me erase and get a little bit of space here. In terms of predicting, for the bonding test, you need to understand the definitions, what a Lewis acid and Lewis base is, and that type of thing. But iron 3+ reacts with thiocyanate, SCN-, but it only takes one of them. Just have to memorize it. I don't know what else to tell you. It's beautiful too. That's one of those ones you should start nagging me right now. Notice I have a 2 positive charge left over, 3+ -1. Nag me right now to show you because it's this beautiful blood red. So it's really pretty cool. Okay. Another exception would be is if I had aluminum metal. Okay, and I added hydroxide to it. Since the aluminum gets oxidized, I'm going to make the same complex I did before. Again, because AP accepts both 4 and 6, so let's make it easy and just double the charge. But since the aluminum went from a 0 charge to a +3, something has to be reduced, and it's hydrogen in the water primarily. Lots of hydrogen around in the solution. Okay, so we're not going to worry about balancing this one right now. It's a little more complex, and talk about complex ions. It's a little more complex than I want to get into. So we're not going to worry about balancing it. I just wanted you to see that, and we'll have a day where we work on predicting these. Now, the last thing I want you to see is that both of these have an AB6 structure. So both of these would have an octahedral structure associated with them. Okay, that's it. So hopefully I will do problems similar to this. This happens to be a direct AP question, so I will likely modify it. So until then, assuming I get the time to do that, this is signing off.